Hey guys, today we're going to talk about acceleration. Sorry we couldn't do this in person. The PowerPoint that we have on Schoology isn't my favorite thing that I've ever made, so instead I figured I'd send you a video this way, and hopefully this helps alleviate some of the problems that we will have in the future when it comes to acceleration. So this is technically 2.2, Chapter 2, Section 2 and 3 put together with some other parts edited out, just to hopefully make sense and break it up into smaller pieces. All right, so we're going to start talking about the fastest things, or acceleration, what causes acceleration, how things change their velocities and or speeds. So first, to model acceleration, let's stop and think, what are the fastest things that you can think of? Make a list of 10 things. So what are the fastest things you can think of? List 10. Okay, so as you list 10, take a second to pause the video and list out 10 things. It doesn't have to be in order of, fastest to slowest or whatever. Just list 10 things that go really, really, really fast. Okay, now that you've made your list of 10 things, I want you to think about what makes them fast. What makes an object fast? Does the rate that they speed up affect how fast they are? These are things that I want you to think about as we go through this, okay? So, after you've made your list and you've thought about, what makes them fast, how they speed up or slow down, is that what makes them fast? We're going to talk about acceleration. And acceleration is the rate of change in velocity with respect to time. Okay, so acceleration, that's just the definition of acceleration. I believe it is the same as the definition of your book, but acceleration is the rate of change in velocity with respect to time. What that means is we can show that algebraically as little a for acceleration is equal to delta v over delta t. Now that little triangle means delta, and that's the Greek symbol for change. So we could say, and that's important to know because we're going to use this same symbol for the rest of the year, so you might as well get that in your head, that the little triangle there is, it's not actually a triangle, but we just write it as a triangle because it's easier, but it is the Greek symbol for delta, which is the symbol for change. So that means that if acceleration is equal to the change of velocity over the change of time, that means we can change our velocity by finding the final speed and subtracting the initial speed and dividing by the same thing for time. I'm just going to be lazy and I'm going to write delta t on the bottom. Okay, so VF equals final speed. I shouldn't write speed, I should be saying velocity. And VI is the starting velocity. The I stands for initial, but sometimes when I say initial, it doesn't always make sense, so using starting velocity or speed helps. Okay, perfect. So this is our main equation. This is the equation that is on your formula sheet that I gave you. It's also broken down into this little addendum so you can know the difference or what these parts actually mean. But that's just how we're going to calculate velocity or acceleration. All right, some other notes about acceleration is that acceleration is measured in meters per second squared. So measured in m/s squared. All right, maybe we can write this with a smaller pen. Meters per second squared. Now, in note of that, meters per second squared does not mean that you need to take something in an equation and divide out and square. This is just a label. It's a unit, just like saying miles per hour or whatever. So you don't need to actually divide, square anything out. That's just the label of acceleration. If you were speeding up and accelerating, you had a plus 10 meters per second squared. That's just telling you an example of an acceleration. You don't actually have to multiply, divide, or square root anything. So don't get confused on that part. The other important piece for acceleration is that acceleration has both direction and magnitude. So acceleration has both direction and magnitude, which means that it is a blank quantity. What's the blank for? I'm asking basically, is it a scalar or a vector quantity? You know that vector quantities have both direction and magnitude, so this is a vector quantity. All right, so when you have your object, whatever it is, here's my car, and it's accelerating, it is going to be accelerating at its plus 10 meters per second squared. Okay? The arrow represents the direction, and the plus 10 meters per second squared is its magnitude. All right? So it has a vector quantity of which direction it is going. Now, we can also represent this on graphs. I know you guys love graphs because we were doing a whole bunch of stuff with graphs before you left, and then in your last lab that you had to do, we were making stuff with labs. So in our graphs, we are going to have our velocity and time graph. Because acceleration is our rate of change with velocity in respect to time. So we have a couple different points in our velocity time graph. If we are climbing, and we're going to have a flat line, and then we're going to have something that just trickles down like that. At point A, we're going to have point A, point B, and point C. All right, so this is our velocity and time graph. We're also going to write here, let's make this clean. We're going to have a point, we're going to have the motion, and then we will have the meaning. And I'm going to start writing this. Okay, so at point A, our velocity is changing with respect to time. So as it is moving upward in direction, we have a positive acceleration. It is positive because it's moving up on the graph, away from our starting point, up and away, which means that we are speeding up. All right, at point B, we have a flat line. All right, so our point and velocity is not changing, but time is changing. So if we're not changing our velocity, but we are changing time, we are going a constant speed. And at point, oops, that should definitely be a C. As we're changing our velocity in the negative with respect to time, so we have negative acceleration. That means we are slowing down. Which is pretty simple because your velocity is going lower over time, which means that you would be slowing down. If you were working and you're driving your car right here at point A, you are speeding up, you're pressing on the gas pedal. At point B, you're going a constant speed, so we can say that you're using your cruise control. And at point C, you're slowing down, so you're using your brakes, so you're coasting to a stop, or at least to a slower speed than what you were currently going. All right, so that's acceleration in a nutshell. Really pretty simple concept to work with. We've been doing a lot of this. You've seen a lot of this in your entire life. It's not new. It's not crazy. What you might not have spent a lot of time with is how gravity and acceleration interact together. So this is actually technically section 2.3 in your book. It has to talk about falling objects. Okay, so we're going to talk about falling objects real quick. And why this is important is because acceleration applies to changes in direction, right? If you're traveling in a car around a curve, you feel the effects of acceleration because you're changing its direction, maybe not necessarily its magnitude, all right? So this is why acceleration affects velocity and not speed, because it has that direction. Velocity has that direction, so therefore acceleration has that change in direction. Okay, so we're going to write acceleration applies to changes in direction. This is why acceleration, again, affects velocity and not speed. Okay, so if this acceleration is going to apply in changes of direction, we can think of this in terms of free fall, or things dropping and changing their direction, right? So if an apple falls from a tree, does it accelerate while falling? Yes, all right? Then you have to think about and frame it in the way as, does the height from which the apple falls affect its speed when it hits the ground? Also, yes, makes sense. The higher up you go, the faster it is falling on the way down, all right? So free fall is determined by an object affected only by gravity. Okay, and when I say only by gravity, that's the important part. Only by gravity. Now there's a lot of things, oh, Mr. Ranger, isn't everything affected by gravity? Yes, of course it is. But I'm talking only by gravity. When you jump out of a perfectly good airplane and you are dropping down towards the ground, you're only being affected by gravity. Yes, there's air resistance, but we're going to talk about that in a little bit later, okay? Objects that move through space, only by gravity. Things like in that regard, okay? So, when they're only being affected by gravity, they're being affected at acceleration at a rate of accelerated at a rate that we call g. If you remember 9th grade science, g is equal to 9.81 meters per second squared. Now that is a number that you need to memorize in your brain. 9.81 meters per second squared. It's going to be used a lot. Okay, so you need to get that stored into your brain somewhere. When we talk about gravity acceleration, 9.81. All right, so all objects, doesn't matter what it is, on Earth fall at the same rate. Okay, all objects on Earth fall at the same rate. And what is that rate? That rate is here, right here, 9.81 meters per second squared. But then you say to yourself, Mr. Ranger, if I take 2 pieces of paper and I crumple one up and I leave another one flat and I drop them, they don't fall down at the same rate. And you're right, they don't. If we can neglect air resistance. Okay, neglecting air resistance. Surface area has a big thing to deal with gravity, surface area, and air resistance. The more surface area you have, the more air resistance. So the slower that you fall, that's the whole basis of a parachute. So I get that this is going to be affected, but as we look at our stuff in physics and acceleration, we're going to neglect air resistance for small traveling objects because it's kind of negligible. You don't get a lot of air resistance as things go flying around like this. All right, so now we need to look at how to find how fast an object is traveling after falling a distance. All right, so we're gonna go with, I'm gonna write in a smaller pen again, to find how fast objects travel after falling a distance. Okay, so to find how fast an object travels over distance, you're going to go with your velocity. This is most likely in the y direction, but we'll just leave it as velocity right now, is equal to gravity times time. All right, that's how fast. Okay, so our velocity, I'm going to put a little Vy there because it's probably, you know, we're only talking about one-dimensional motion, so how fast it's going to fall after a distance. If you know how long it's in the air, you can figure out how fast it is going. All right, to find out how far. Figure out how far an object falls, we're going to go into some interesting equations soon called the Big Four kinematic equations, and this is a part of a kinematic equation. To figure out how far an object falls over a set period of time, you're going to take 1/2 times gravity times time squared. Now, order of operations dictates that you are going to square time before you multiply it by gravity in 1/2, but to figure out how far an object falls, this is what you need. Okay, this video is getting to be a little bit long, which I'm sorry about, but the information's out there. Something that you guys do need to get done this week is you do need your book. We're going to read page 48 through 64, and there's going to be some acceleration practice problems on Schoology. There's only 16 of them. They are not super difficult. They are just algebra problems. Your acceleration practice problems will look like this. Make sure that you answer all the questions fully. It says you must show your work. If you use a calculator, that's fine. I don't care, but show how you did it so I can track and see if anything needs to be fixed. So I hope you guys have a great day, and we will catch you later.